Okay, by the way, it's actually the first paper that proved that shortest job first ranking is optimal in a single server queue, I think. So it's a fun paper to read. It's an old one. So how do we actually compute these shortest stall time how do we actually compute the stall time for each thread such that we can find the shortest stall time threads? So we're going to look at, the memory controller looks at two different values for each thread. One is the maximum number of mark requests to any bank. I'll call this the max bank load. This is, and we're going to rank the thread with lower max bank load higher. I'll show you an example. Because if a thread has a maximum bank load that's high, it means that it has a long stall time, right? If it's low, it has a short stall time, very likely. And the memory controller also looks at total number of mark requests. It computes that. We'll call this the total load. And this is used as a tiebreaker. We're going to rank the threads with lower total load higher at the memory controller. Let me give you a pictorial example that's a little bit more complicated. You have 4 banks and 4 different threads. And I'm going to assume that everything is a row conflict here. The paper is an example with row hit. There's a row buffer, and you get row buffer hit requests. So let's compute these two values for every one of these threads. Let's take thread 0. Thread 0's max bank load is 1 because the maximum number of requests it has to any bank is 1, right? And its total load is 3 because it has 3 requests to all banks. Thread 1's max bank load is 2 because the maximum number of requests it has to any bank is 2. It has 2 requests to bank 0, right? And its total load is 4. Thread 2's max bank load is 2 also because the maximum number of requests it has to any bank is 2 to bank 1 and bank 2. And its total load is 6. And thread 3's max bank load is 5 because it has 5 requests to bank 3. And its total load is 9. So now that we have these two values, we can rank these threads based on these rules. Thread 0 is ranked higher than thread 1, ranked higher than thread 2, ranked higher than thread 3. Because max bank load of thread 0 is the lowest, right? And these two are ranked such that total load breaks the tie of the max bank load. And this way we can achieve a shortest stall time first ranking. Again, this is not perfect because the stall time depends on the scheduling also, right? And we're not going to take that into account. We're not going to take everything that comes before a thread into account. We're doing this independently for each thread. So let's take a look at what happens with this ranking. So this is our baseline scheduling order. We're assuming that we're servicing requests in the arrival order, and this is the arrival order. And I'm assuming that this is the time each request is serviced. If you use this baseline scheduling order, this is what happens. I'm going to assume that I don't take into account the bus delays. There's only the bank latencies. If you look at this order, let's take a look at the stall times of each thread. For thread 0, its last request is serviced after time 4, so its stall time is 4. For thread 1, its last request is serviced after time 4, so its stall time is also 4. Thread 2, its last request is served after time 5, its stall time is 5. And thread 3, its last request is serviced after time 7, so its stall time is 7. So the average stall time is 5 bank access latencies in this case, if you do the computation. What happens with parallelism over batch scheduling? Within this batch, now we're going to not use this arrival order, but we're going to rank the threads this way. T0 ranked higher than T1, ranked higher than T2, ranked higher than T3. So the controller prioritizes T0 within this batch. So T0's request will be prioritized across all banks. As a result, it'll look like this. Its last request will be serviced after time 1. Then T1 is prioritized at the priority order. So its last request will be serviced after time 2. Then T2 is prioritized. Again, each bank does this in a priority order. So you actually kind of fill in the blanks that happen. So T2's last request is serviced after time 4. And then T3 is the lowest priority, lowest ranked thread. Its last request is serviced after time 7. As a result, you get 3.5 bank access latencies as opposed to 5. And if you look at this schedule, this is much more regular than this schedule. This way, thread 0's parallelism is perfectly maintained. Thread 1's parallelism is maintained mostly. And thread 2's parallelism is also maintained as best as you can, given the other threads. And thread 3 is just, it's also maintained, but it's deprioritized, right? So that's how you can reduce the average bank access latencies, average stall time of each thread. What's the scheduling policy, resulting scheduling policy? Basically, it looks like this. Mark requests are prioritized over all others. This is the batching component. And this is the rank parallelism array within batch scheduling component. So we prioritize row hit requests over others to exploit locality. And higher ranked threads are prioritized over others to exploit bank level parallelism, to do shortest stall time first. And the last priority order is oldest first, to break the ties. Now there are three properties here. It exploits row buffer locality and also intra-thread bank parallelism. And these are actually at odds with each other. So if you might ask the question, why do you do this first and do this next and not the other way around? Well, because there's always a trade-off between locality and parallelism, and we don't have a good solution to get the best of both worlds here. So if you do it the other way around, if you prioritize higher ranked threads first and then row hit request first, it's similarly well performing. The second is this scheduling policy is work conserving. So if you have an unmarked request to banks without marked requests, remember this is just a priority order. If there's no marked request, then row hit requests are prioritized. So you don't waste bandwidth. If there's bandwidth available, then you use that bandwidth for marked requests or unmarked requests in a priority order. And marking cap is important. So marking cap determines how many requests are marked, how many requests are in the batch, right? If it's too small, if your marking cap is too small, then you have a smaller batch, which means that you're actually putting fewer requests from a thread into the batch. As a result, you reduce the row buffer locality of the thread. You're not exploiting the row buffer locality well because you're switching to some other thread quickly. If it's too large, then you have lots of requests from a thread in this batch. The problem with this is if you have a memory non-intensive thread, when it arrives, it needs to wait for this long batch to finish first. As a result, you penalize memory non-intensive threads. And we've played with a lot of different policies. If you actually look at the paper that has mechanisms that try to sneak in some requests into the batch such that these threads are not penalized, but none of them are that great because you lose some starvation freedom as you do that. So there are many more trade-offs, and those are analyzed in the paper. What is the hardware cost of all of this? Basically, with an 8-core system with a 128 entry memory request buffer, we get less than 1.5 kilobyte storage cost. And we don't have any complex operations anymore. Divisions that were needed, at least approximate divisions that were needed in stall time fair memory scheduling are actually gone now. And this is not on the critical path. Memory scheduler should not be on the critical path. Scheduler makes a decision only every DRAM cycle. And you can actually make it coarse grain, as we will see in the next work. So let's take a look at some performance results. Actually, this is the unfairness results. This is for 4-core systems, 8-core systems, and 16-core systems. And I'm going to look at 5 different schedulers. The first one is first ready, first come, first serve. That's the row hit first scheduler. The second one is first come, first serve. That's basically no scheduling, right? Oldest first. This is adaptation of fair queuing techniques used in networks to the memory scheduler, network fair queuing based scheduler. The stall time fair memory scheduling and parallelism over batch scheduling. And y-axis is unfairness. Unfairness is, remember, maximum memory slowdown divided by minimum memory slowdown in the system for any thread. And lower is better in the unfairness. Ideally, unfairness is 1, right? And for the baseline scheduler, unfairness is pretty bad. It's, these results are averaged across a very large number of applications, which are described in the paper. For the baseline scheduler, unfairness is pretty bad. Let's take a look at a 16-core system. For first come, first serve doesn't solve the problem. Network fair queuing actually doesn't solve the problem because it's actually not aware of this bank level parallelism, as well as not aware of the banks itself. And stall time fair memory scheduling reduces unfairness significantly compared to these past schedulers. And parallelism over batch scheduling reduces unfairness even more. And that's consistent across different types of systems.
So are these results after you make your manipulation with the memory cap?
That's right. So here we take the best memory cap. So it's a static memory cap. We haven't explored dynamic memory caps, which is very interesting, I think. We've explored some potential ways of sneaking in requests, even though a thread has exhausted. So you form a batch, and when you form a batch, a thread may not have any requests, right? But it may have requests later. Then the question is, do you actually put those requests into the batch? If you do that, now you go into a slippery slope, because that reduces your starvation freedom guarantees. We've explored mechanisms, but we haven't found anything great in that area. But potentially you can get better with dynamic marking cap determination. So what is that's the benefit compared to stall time fair memory scheduling. So what is the benefit on system performance? Again, these are 4-core, 8-core, 16-core systems. This is normalized performance, normalized to first ready, first come, first serve. If you look at this, performance improvements of stall time fair memory scheduling is significant compared to best previous scheduler. And parallelism over batch scheduling also improves performance on top of stall time fair memory scheduling. And there are two reasons for this. One is because parallelism over batch scheduling preserves parallelism, it actually reduces the average stall time of each thread. And as a result, performance improves. And the second is, this also improves fairness. It's more fair than stall time fair memory scheduling. As a result, core utilization improves. So you get better system performance due to two reasons. Any questions? Okay. I guess I'll continue with upsides and downsides. This is a good exam question, by the way. But so the upsides of this is, this identifies the notion of bank parallelism destruction across multiple threads. I think that's the interesting part. You have bank level parallelism destruction that serializes the requests of a thread. And this becomes much higher as you add more threads and more banks into the system. So I've shown you an example with 2 threads, but you can construct the example with 4 threads and 4 banks. And it becomes, every thread can be serialized for a very long time. And if you're much more regular, you get much higher benefit. It's a simple mechanism. It's much simpler than stall time fair memory scheduling. And certainly batching is very simple, and ranking is relatively simple also. The downside is, as I will show you, if you actually want to implement this in a system with multiple memory controllers, this is one downside, you get too frequent coordination. So the idea is, how do you compute ranking across multiple memory controllers? Right? A thread may have requests across many different controllers. Now these controllers need to be aware of each other. If you're computing this ranking at every batch boundary, how do you synchronize the batches across different controllers? So we're going to try to get rid of this problem by coarsening the intervals. And you will see this in the next work. The second and perhaps more important problem is it doesn't always prioritize the latency-sensitive applications. Right? Latency-sensitive application, whenever it has a request, it still needs to wait for the batch to be complete. But that may not be needed. Right? Maybe you don't batch these requests. Maybe you do something else. So we're going to try to solve these two problems. My focus will be, you could actually read the paper as to how you can reduce the coordination, but I'll not talk about that in detail in the next one. Any questions? Okay. So some of these concepts actually will be similar to operating system scheduling concepts also, especially with this work and the next work. And I think they are similar actually, and it's interesting to look at how these different scheduling techniques at the operating system level can be coordinated with the scheduling techniques at the memory scheduling level. And maybe a lot of the scheduling that we have at the operating system is going to move down to hardware as we go forward. Because a lot of these operations of scheduling need to be done at very, very low overhead as you switch, as you have many cores and as you want to exploit locality and parallelism between the cores. So the next work is Atlas memory scheduling. This is my student Yoongi Kim's, some of his ideas with Dongsu. Basically, if you think about memory scheduling, a thread alternates between 2 states from the point of view of a memory controller. This is time as you go here, and on the y-axis we see outstanding memory requests. You have the compute episode where there's 0 outstanding memory requests. As a result, during this time the thread makes fast progress. It has high instruction level parallelism, IPC. There are also memory episodes where the thread is waiting for at least 1 request. These are non-zero outstanding memory requests. The thread is making very slow progress in this case. The goal of a memory scheduler is to minimize the memory episodes, the time spent in memory episodes in the entire system. So how do you actually do that? So we would like to prioritize the thread whose memory episode will end the soonest at any given point in time. This minimizes the time spent in memory episodes across all threads. This is actually supported by queuing theory. If you've taken a scheduling theory class, you probably know that shortest remaining processing time scheduling is optimal in a single server queue. Now we're not going to be a single server queue, so we're going to remove the optimality claim here. But basically, if you have multiple different jobs that are accessing a single server queue, you'd like to pick the one that has the shortest remaining processing time at any given time to maximize job throughput. We'd like to take that idea and apply it to memory scheduling. Then the key question, if you look at this, so we'd like to minimize, prioritize the memory episode that has the shortest remaining processing time, right? Then the key question is, how do we know the remaining length of a memory episode? We know when a memory episode begins. The memory controller knows when a thread starts generating requests because it can keep track of that. But it doesn't know when its thread will stop sending requests, right? So how much longer will this take? So what we've discovered is that past is an excellent predictor for future in this case. So if a thread has been generating requests, this is the attained service of that thread for a while. This is the past. And we're going to define the remaining service as the future. It turns out the remaining service correlates with attained service. A large attained service leads to large expected remaining service. This is purely empirical based on the analysis of the workloads. Why? Well, I'll give you a statistical result. Basically, memory episode lengths are Pareto distributed. It's a heavy tail distribution. This is one example. This is the memory episode length, x in cycles. And this is the probability of the memory episode being greater than x at any given time. And if you look at this, if you plot this in a log-log scale, you get a linear curve as you get rid of some of the irregularities. And this shows you that this is a Pareto distribution, which means that the attained service correlates with the longer an episode has lasted, the longer it will last further, which means that the attained service at that point in time, or how long a thread has remained over there, is correlated with how long a thread will remain there. So people have actually discovered this in many different systems contexts. This is actually interesting, I think. So people have found that, for example, the file sizes that are transferred over FTP protocol are Pareto distributed. Basically, if you transfer for long, you're going to transfer for much longer. If you transfer it for a short time, it's likely that you're not going to transfer for a long time. My favorite example, I don't know if people have studied this, but it's sleep. If you've slept for a long time, it's likely that you're going to sleep for longer. If you've slept for a short time, it's likely that you're going to sleep for shorter. I don't know if that works perfectly, but that's the idea here, basically.
But that might change over time. So you cannot make such an estimation for all lifetime of the system. This might change with respect to time.
That's right. Yes, exactly. That's why we're going to try to do an adaptive policy. Mm-hmm. We're going to use attained service-based scheduling. It may not be correct for all workloads. That's right. Okay, so that's the idea basically. Attained service correlates with remaining service. So if you favor least attained service memory episode, it amounts to favoring memory episode which will end the soonest. And the hope is that that will maximize system throughput because it's minimize the amount of time the system will spend on these memory episodes. So let me cap a little bit. The idea is least attained service memory scheduling, and this is not new to the systems context, right? Because people have been doing operating system scheduling based on this idea a long time ago. It's not perfectly that way today, but the ideas have been there. So we'd like to prioritize a memory episode with least remaining service. And queuing theory tells that you should prioritize a job with shortest remaining processing time. This is provably optimal in a single server queue. So we found that remaining service correlates with attained service. And attained service can be tracked by a per thread counter. As a result, if we prioritize a memory episode with the least attained service, we can minimize the memory episode time. And actually, there are arrows here, but you cannot see them. So if you feel why is it happening this way, there are invisible arrows here that lead to, actually there's an arrow from here to here, and there's an arrow from this progression. Maybe next time I come here, we'll have better projectors. Okay, so one downside of this is all nice and supported by queuing theory, but again, it's not optimal because it's not a single server queue. I'd like to emphasize that. And I'm not sure if there's a solution in queuing theory for a system like the memory scheduler, because a memory scheduler is a set of relatively complex queues that also exploit some locality with the row buffer, right? It's not clear how you would model that with queuing theory today, at least. So one problem with this is this least attained service scheduling does not consider long-term thread behavior. And we'll see that this is an issue. Let's take a look at this. And this is actually a problem because we formulated the problem in a way that's memory controller centric. And maybe we'll get back to that. Basically, if you look at this, if you look at the short-term thread behavior, a thread has short memory episode, another thread has long memory episode. Least attained service scheduling says prioritize this thread, right? This has short memory episode. But if you look at the long-term behavior, if you have a bigger picture, this thread may go back to a very short compute episode and then go back to the short memory episode again, right? Whereas this thread, after it finishes its memory episode, it'll compute for a long time. You would really like to prioritize thread 2 in this case, right? Because it's more beneficial, because it results in very long stretches of compute episodes where this thread's memory episodes can be serviced, right? So we'd like to do that. And the reason I'll get to it, ideally you would really like to prioritize the threads that have long compute episodes rather than short memory episodes. So that's the formulation of the problem, I think. We formulate the problem from the point of view of the memory controller, not the system itself. So going forward, we'll try to fix this problem in the next work. Basically, we would like to prioritize threads that have long compute episodes. That's why we're trying to fix it over here. So if you look at the short-term thread behavior, you look at this, a single episode, but we'd like to have a longer view to avoid the problem that I've showed you over here. We'd like to consider the long-term thread behavior. So we'll have a quantum, and we'd like to we'll keep track of the attained service over millions of cycles. And so how does this work? Once you have a quantum-based attained service tracking, during a quantum, each thread's attained service is tracked by the memory controllers. This is ASI. A thread's attained service during only the ith quantum. And at the end of the quantum, each thread's total attained service is computed as a weighted sum of the attained service in the previous quantum and the total attained service in all of the past quantums. So you get a total attained service across the entire execution of the thread. And this weighting determines how important the last quantum is compared to the entire history. And you can actually use this to figure out how much of past history you take into account. And after this, threads are ranked, and threads that have lower attained service are ranked higher, because we want to prioritize the threads that have attained least service. In the next quantum, we use that ranking, to schedule the threads. And again, we do ranking to preserve bank-level parallelism, right? Okay, so this is the scheduling algorithm. It's called adaptive per thread least attained service. And this is the request prioritization order. First, to prevent starvation, requests that have been outstanding for a long time, where long is like 10,000 cycles or 5,000 cycles, are prioritized over others. This doesn't happen much in our experiments, but you really need something like this, because we're really prioritizing threads based on attained service. And in the worst case, we could actually prioritize starve a thread. The second ranking is to maximize performance. We prioritize threads based on least attained service order, rank order. Third, priority order to exploit locality. We prioritize row hit requests over others. And for tiebreaker, it's the oldest request over others. Okay. So there's also the question, how do you actually coordinate memory controllers to agree upon a consistent ranking? This is actually interesting, but I'll not tackle that here. And this basically, the idea is the memory controllers exchange information and send it to a centralized memory controller that determines the entire ranking. And this because the quantum granularity of millions of cycles, that's not a big problem, because you only send requests very infrequently to compute the ranking. That's another benefit of a long quantum, right? You can do coordination across different in a distributed system. Okay. So how does this impact performance? These are results on a 24-core system, again averaged across a large number of workloads. This is system throughput. And we see number of memory controllers increasing over here from 1 to 16 in a 24-core system. So bandwidth is increasing a lot. And this is normalized. It's actually not normalized system throughput, but this is system throughput. We look at several schedulers, no scheduling. First ready, first come, first served, total time fair memory scheduling, parallelism over batch scheduling, and Atlas. If you look at this, Atlas consistently provides higher system throughput than all previous scheduling algorithms. the performance compared to the best previous algorithm, which is parallelism over batch scheduling, is 8.4% here with 4 controllers. And as you actually reduce the number of controllers, which means that the system is becoming more bandwidth limited, right? You have 24 cores banging on a single controller. The performance improvement is high. You would not build a system like this. It's a bad design. But Atlas becomes a more efficient scheduling policy as bandwidth becomes scarce. And here, if you look at 24 controllers and 24 cores and 16 controllers, you see that our performance improvement is very low. But scheduling policy doesn't matter that much over here. If you look at this, performance is very high. If you have, this is a very expensive system, right, with 16 memory controllers. And this is the system throughput in a 4 memory controller system as we vary the number of cores. Number of cores is varied from 4 to 32. This is the best previous scheduler parallelism over batch scheduling and Atlas. As you increase the number of cores, Atlas becomes higher performance. Its performance improvements increases. Again, this is a more bandwidth efficient scheduling policy as you increase the number of cores. Basically, as the amount of bandwidth per core reduces, Atlas becomes more efficient. Okay, so what are some of the properties of this, what I've described? Basically, our goal, we had several goals. We wanted to maximize system performance, and there are several properties of Atlas that try to do this. Least attained service ranking tries to maximize system performance by minimizing the amount of time system spends on memory episodes. Preserving bank level parallelism is enabled by ranking the threads, and we try to locality as best as possible by prioritizing row hits over others. This is actually scalable to a large number of controllers because it requires very infrequent coordination because of the long quantum, as I discussed. And it's configurable by system software. What you can do is you can scale the attained service with the weight of a thread. So the memory controller can, the operating system can communicate the weight of a thread as its priority. And we can change the attained service with that weight. For example, if a thread is very, very important, what you can do is you can divide the attained service with the weight such that attained service looks like 0 for that thread. And that thread is always prioritized. Right? If a thread is not that important, then its weight will determine what its attained service looks like to the memory scheduler. So it's low complexity. Attained service requires a single counter per thread in each memory controller. And that's the main cost, main hardware cost of this. Okay. So before going into the next work, let me talk about the upsides and downsides of this. Upsides, this is actually very good at improving system performance. It is low complexity. It's the lowest complexity scheduler that I described so far. And coordination among controllers happens infrequently. The downsides, well, it's not fair, actually. I'll show you some results. Lowest ranked threads get delayed significantly. In fact, not always the lowest ranked threads. Sometimes the medium ranked threads get delayed very significantly. As a result, this is unfair. If you want to maximize system performance, this may be good. But ideally, we would like to get the best of both worlds. So we'll try to do that in the next policy. But shall we take a break before this or after this? Okay, after this. This is a good progression. And after this will be a good natural break. But I see people are getting tired also in the back. What do you guys want? Break or?
I prefer continuing.
Okay, let's finish this. At least you'll get the key ideas, and then we'll move on to a different way. So basically, after Atlas, we see that this is good at improving performance, but it's not fair. We'd like to get the best of both worlds. And how do we do that? So let's take a look at what we've studied so far. I'm going to plot the scheduling algorithms based on their system throughput across 96 workloads in a 24-core system with 4 memory controllers. System throughput is this way. It becomes better to the right. And this is the fairness metric, which is maximum slowdown. I've changed the fairness metric because this is, I believe, is a better fairness metric, and I can point you to references related to this. Basically, the fairness is defined as maximum slowdown in the system. You look at the slowdowns of all threads and take the maximum slowdown as the fairness. This also takes into account performance a little bit, but if you do maximum slowdown divided by minimum slowdown, you sometimes penalize threads. Whereas here, if the maximum slowdown is high, you're not fair. If the maximum slowdown is low, you're more fair. So better fairness goes down this way. Ideally, you would like to be here, right? Higher throughput, higher fairness. Atlas actually has a system throughput bias. It sits here. You don't see the bias here, but as I populate this, you'll see the bias. Parallel memory batch scheduling sits here. It has not so good system throughput, but much better fairness because it does the batching. And its ranking scheme is different from Atlas. It's finer grained. Stall time fair memory scheduling is not in the Pareto optimal front, if you will. It's not good for system throughput or fairness at the same time. First ready, first come, first serve. Row hit first scheduling that's employed in many systems today is here. And if you do first come, first serve, I guess it got lucky in terms of fairness over here. It's not always this lucky, but for these workloads it got lucky. It's pretty bad in terms of performance. So ideally we would like to get over here. But no previous memory scheduling algorithm provides both the best performance and system throughput. Let's take a look at how these different policies operate at some level. The throughput biased approach says you would like to prioritize less memory intensive threads to maximize system throughput. Why? Because a memory intensive thread, a thread that's not memory intensive has the most potential to make progress in its core and keep it utilized, right? Again, if it has single request, after that it keeps its core utilized for a long time. Whereas a memory intensive thread keeps generating lots of memory requests, so it stalls for a long time. Even if you prioritize all of its memory requests, it's going to be slow anyway. So this says that you should rank the threads this way and prioritize less memory intensive threads. This is good for this thread, but it's bad for thread C because it starves, especially when you have many threads in front of it. Right? It's actually bad for medium threads also. The fairness biased approach, one fairness biased approach says the threads should take turns accessing memory. Right? This is, if you do this, it's a round robin order. The thread C does not starve because it'll get its turn every time. Whereas thread A, this is not good for, it's not prioritized. As a result, you get reduced throughput. Right? So the realization is that a single policy that's uniform across all threads is not sufficient. So we're going to try to achieve the best of both worlds with heterogeneity. So for throughput, the realization is that we would like to prioritize memory non-intensive threads. For those threads that are memory non-intensive, we're going to somehow figure them out and prioritize them. For fairness, we found that unfairness is really caused by memory-intensive threads being prioritized over each other. So unfairness is not caused by these little threads being prioritized over the big threads, because these generate requests infrequently anyways. It's really caused by these big elephants stomping each other. Right? Elephants are fighting with each other here. The mice do not affect the elephants. So to solve this problem, we'd like to shuffle the thread ranking. We'd like to be fair across these threads. And we've also found that memory-intensive threads have different vulnerability to interference. So we'd like to do this shuffling asymmetrically. Instead of every thread getting to the top position at an equal priority, we're going to have some threads get to the top position with higher priority, some threads with lower priority, because some have more vulnerability to interference and some are less vulnerable to interference. Some threads are nicer, some threads are not so nice, basically. You could think of it that way. And we'll define a niceness metric for the threads, and based on that, do the shuffling asymmetrically. So that's the key idea here. We're going to group the threads into two clusters. Out of all the threads into the system, we're going to take the memory non-intensive ones and memory intensive ones, group them separately, prioritize the non-intensive cluster over the intensive cluster to maximize throughput, and employ different policies in each cluster. For the non-intensive cluster, we're going to prioritize threads based on their miss rates, based on their memory intensity. Less intensive threads prioritize over others, although it doesn't matter that much over here. For the intensive cluster, this prioritization policy matters a lot because you're dealing with fairness issues with big threads. And we're going to shuffle the ranking of different threads such that each thread gets to be higher priority at any given point in time. So let's take a look at how we do these in some detail. How do we do the clustering? So this is the outline of thread cluster memory scheduling. First, the memory controller sorts the threads based on misses per kilo instruction. This is the miss rate, how intensive threads are. And computes a total memory bandwidth usage for the threads for a quantum, for a time quantum. And forms a non-intensive cluster as those threads that consume a fraction of that total memory bandwidth usage. And that fraction hopefully is small. Basically, alpha t, all those threads that consume some fraction of the memory bandwidth are considered non-intensive. And alpha, as we will see in our experiments, will be 10%. And we'll see a trade-off between throughput and fairness as you change the value of alpha. Well, that's the cluster threshold. The rest will be deemed intensive threads. So what do we do between clusters? Basically, we prioritize non-intensive cluster. Again, as I told you, this increases system throughput because non-intensive threads have greater potential for making progress. And this doesn't degrade fairness because non-intensive threads are light. Now, this is not exactly correct, actually. This is correct if you do the clustering right. If you do the clustering wrong, such that a heavy thread escapes into this cluster, then this degrades fairness a little bit.
So you have to select your alpha in a nice manner.
Yes, that's right. You have to either select your alpha in a nice manner or somehow be more intelligent. But whenever you have a single threshold dividing two clusters, you always have issues. You always have that granularity problem, right? So we won't be perfect. This will be the Achilles heel of thread cluster memory scheduling. It'll perform really well, but the downside of this will be it'll be not so robust because of this cluster threshold. Sometimes it'll do great, sometimes it won't do so great because sometimes the thread will sneak in here that's intensive. Okay. So what do we do in the non-intensive cluster? We prioritize the threads according to their MPKI. The threads that have the lowest miss rate are prioritized higher. This increases system throughput because least intensive thread has the greatest potential for making progress again. But again, as I said, these are small threads. So this should not normally matter. So if you do random prioritization across these threads, again, it doesn't matter that much, except if you did the wrong decision in clustering. Okay, let's take a look at the intensive cluster. I'm going to spend the most time here because this is what affects performance and fairness most. As I told you, we will periodically, the memory controller periodically shuffles the priority of the threads. So it looks like this. Every thread gets to be the top thread at any point in time. This increases fairness, but it turns out treating all threads equally is not good enough. Because threads have different behavior. Threads are not homogeneous. They're heterogeneous in their behavior. Equal turns do not lead to the same slowdown. Let's take a look at why this is the case. We've run experiments with two intensive threads, and we're going to get back to random access and streaming. These are two ends of the spectrum, right? It could be purely random access, purely streaming. Which one slow down more easily?
Random access.
Random access. That's right, exactly. And I'll give you why. So I'll give you the results first. If you actually prioritize random access, streaming thread slows down by about 7x. And this is a contended study. That's why the slowdowns are really high. If you prioritize the streaming thread, random access slows down by much more, 11x. And which means that a random access thread is much more vulnerable to interference, whereas a streaming thread is much less vulnerable. Or put another way, random access thread is a nicer thread. If you prioritize it, it's much nicer to the streaming one. Whereas streaming thread is a bad thread. It's not nice. It slows down other threads much more. So why is this different? I'll just give you the intuition. Let's take a look at, this is memory with multiple banks. Random access threads for equal memory intensity, it spreads its requests to different banks, right? And these go to different banks. And they activate different rows. And all requests are parallel. It has high bank level parallelism, right? Whereas a streaming thread keeps sending requests to the same bank for a while. So it activates a row and does this, right, as I've shown you earlier. Basically, it has all of its requests go to the same row in a bank, and it has high roboflow locality, at least for a while. So if you run these two together, what happens is if you prioritize a streaming thread, what happens is streaming thread gets to this bank and hogs it for a while, whereas random access thread goes to these different banks. Now these three requests are serviced in parallel, but this poor request gets delayed for a long time, right? As a result, the random access thread cannot make progress until the streaming thread gets out of the way. So it gets stuck, basically, which means that this is much more vulnerable to interference. And if you do the other animation where you prioritize the green one, the random access thread gets out of the way of the streaming thread very quickly, right? Because there's only one request to bank 3. So it's much better to prioritize the random access thread over the streaming thread. So that's what we're going to try to do in our shuffling. And we're going to we're introducing the metric of niceness. How do you quantify the difference between different threads? Niceness could be high or low. Usually, if you have high bank level parallelism, you're more random access, so you're nicer. This will denote the vulnerability to interference. If you have high row-buffer locality, it's likely that you're less nice because this causes interference, so niceness is low. So we're going to basically take these two values, and I'm not going to go into detail, but basically I have a ranking of threads based on bank level parallelism and a ranking of threads based on row-buffer locality, and we combine these rankings this way to compute a metric called niceness. And we're going to use that metric to bias the shuffling. Let's take a look at what happens with round-robin versus niceness-aware shuffling. What can go wrong with shuffling that's not aware of the niceness of threads? This is the priority of any thread. This is the time interval. And I'm going to show you threads that are nice and that are the least nice. For this interval, the least nice thread is deprioritized. And this is the shuffling interval of threads. How often do you change this shuffling? The most prioritized thread is thread D over here, which is a nice thread. At some point, the least nice thread becomes the most prioritized. And then you shuffle. And you could actually design different shuffling algorithms. And this is what happens if you actually do round-robin shuffling. The good part is each thread is prioritized once. The bad part, if you look at this, is with this shuffling, nice threads interfere lots of interference from this least nice thread. These are the nice threads. They are below the least nice thread for a long time. The area under this curve tells you how much interference the least nice threads actually receive. So with niceness-aware shuffling, we'll fix that problem. Basically, we're going to keep the least nice thread at the bottom for a long time, except we're going to prioritize it once in a while. That's the idea. It's going to stay at the bottom until it gets to the top once every n times, where n is the number of threads. So the good part is each thread is still prioritized once, so even least nice thread gets to inject its request and make progress. But it's not causing a lot of interference to all other threads. In fact, it's not causing any interference except for that interval where it's prioritized over everything else, because it stays mostly deprioritized. Make sense? OK. So that's the idea, basically. I've given you the entire thing. Basically, threads in the system are clustered into two groups, memory intensive, memory non-intensive. And the intensive cluster is deprioritized compared to the non-intensive cluster to maximize throughput. And we have different policies in each cluster. Non-intensive cluster, throughput-oriented. Intensive cluster, fairness-oriented. You shuffle the priority between different threads. And you shuffle this in a symmetric manner such that it considers the niceness of the threads. So this operates based on quantums, as I told you. Basically, the memory controller monitors the thread behavior during the previous quantum, memory intensity, bank level parallelism, and row buffer locality, and uses that to compute the rankings of the threads in the current quantum at the beginning of the quantum. It basically performs clustering, and it also computes the niceness of the intensive threads. And the current quantum is divided into these shuffling intervals that are much shorter than the entire quantum. And you could actually figure out the schedule of the shuffling at the beginning of the quantum, or you could follow a fixed shuffle, so you don't need to figure out the shuffling every 1,000 cycles. This could be all static shuffling. The scheduling algorithm remains simple. Basically, the first priority is highest ranked thread. Requests from higher ranked threads are prioritized, and we've already figured out what are the highest ranked threads, right? Non-intensive threads, the threads in the non-intensive cluster are highest ranked threads. Within the non-intensive cluster, lower intensity threads are higher rank. Within the intensive cluster, we do the rank shuffling. OK. And the row hit requests are prioritized over others after the ranking. And older requests are prioritized over others. So we still exploit row buffer locality as much as possible. What is the implementation cost of all this? Assuming that you already have thread IDs with requests for 24 cores for a given controller, the total cost is less than 4 kilobits. So it's a relatively low cost memory controller. In fact, you only need bank level parallelism and row buffer locality for niceness-aware shuffling. If you do not want to use the niceness, you still get a pretty good scheduler after this. The performance and fairness properties are still quite good. But maybe fairness is not as good if you do not consider this niceness property. And the paper has results related to that. and no computations on the critical path. Let's take a look at how this performs. I've already covered most of previous work, but I'll remind you what those are. The row hit first scheduler is thread oblivious. As a result, it leads to low throughput and low fairness. Stall time fair memory scheduler, when we first started, does not prioritize non-intensive threads. As a result, it has low throughput. I told you that this was a problem with this. The same problem is here also with parallelism over batch scheduler. It has low throughput. An Atlas scheduler leads to most intensive threads to be starved. As a result, it has low fairness. So I've shown you part of this earlier. Row fit first scheduler fits here. Stall time fair memory scheduler here. Parallelism over batch scheduler here. Atlas here. And we wanted to achieve the best of both worlds here. So thread cluster memory scheduler actually achieves the best of both worlds, at least for these workloads. It's a heterogeneous policy, and it gets better fairness than the best previous scheduler for fairness, and it gets better system performance than the best previous scheduler for performance. And it also exposes a nice smooth trade-off between fairness and throughput. When you vary the configuration parameter, all of these schedulers have some configuration parameter. You can change one parameter, and you affect throughput and the fairness. And ideally, you would like to affect it in a predictable way, right? It turns out with the previous schedulers, this is not very predictable. So this is what it looks like. These are supposed to be animated separately. But this is a first ready, first come, first served scheduler. It looks like this. Basically, you can use a parameter. How many requests can you reorder beyond the oldest requests? That's the parameter that is used actually in existing systems. I believe it was first implemented in AMD systems, AMD Barcelona's memory controllers. And they had this parameter where you could cap the number of requests that can be reordered over the older request. And if you do that, you get a weird curve like this. So it's not clear what you would pick here for these workloads. For stall time fair memory scheduling, remember the alpha parameter? If you vary that, you'll get a curve like this. So you're similar in terms of throughput, but your fairness changes reasonably widely. But it's not clear which one you would pick here also. In fact, these are not contiguous also as you increase alpha, interestingly. For parallelism over batch scheduling, marking cap determines where you are in terms of fairness and throughput. And again, your throughput doesn't change that much, but your fairness changes slightly. For Atlas, you change the quantum, how long you compute the quantum least attained services for. And that changes your throughput a little bit, but not your fairness that much. For thread cluster memory scheduling, at least within reasonable bounds of the cluster threshold, you get a smooth curve. And you could actually trade off between fairness and throughput. You could actually be picking any of these values, depending on what you would like. And this allows relatively robust fairness throughput trade-off. And you could expose this to the operating system, and operating system can have different goals, perhaps. So that's cluster threshold. Basically, it's a tunable. What is the operating system support we provide with this scheduler? This cluster threshold is a tunable knob, and the OS can trade off between fairness and throughput. We also have support for enforcing thread weights in this. Again, operating system assign weights to threads, and thread cluster memory scheduler enforces thread weights within each cluster. And it turns out, even if a thread has high weight, even if the thread has low priority, but it's not very intensive, you can still prioritize it without affecting anything else in the system. If it's not intensive, you would like to prioritize that thread because it doesn't affect anything else. I think that's one of the key insights here. So to conclude, no previous memory scheduling algorithm provides both high system throughput and fairness because the problem was they use a single policy for all threads. Thread cluster memory scheduling is a heterogeneous scheduling policy that groups threads into two clusters. It prioritizes non-intensive cluster over others to maximize throughput, and shuffles priorities in the intensive cluster to maximize fairness. And shuffling favors nice threads. Again, this improves fairness even more. And as a result of this heterogeneity, it provides the best system throughput and fairness, at least for those workloads that are studied. So I'll finish this and then take a break, but I'll take questions also before that. There are upsides and downsides to everything in the world, and this also has upsides and downsides. This provides both high fairness and high performance. That's the upside here. The downside is we'll see that this is not very scalable to large buffer sizes. As we put a GPU in the system, this actually floods the queues. That floods the queues, and TCM becomes less effective and becomes non-robust because of the single cluster threshold. And it's well, I've already asked this, I guess. It's not effective in a heterogeneous system, as effective in a heterogeneous system. And that motivated us to do the next work, which is called stage memory scheduling. Any questions until this point? Yes?
Quick question. I think the discussion is centered on performance and fairness. You gave a figure about the cost, but do you have any comparative cost figures between this and the PAR-BS, which seems to be the nearest rival of that scheduling?
So I see PAR-BS and Atlas as both rivals for TCM. So TCM, that's a very good question, by the way. We do have implementations of all of these, but I don't have the results. And I'll give you the high level. TCM is more complex than both Atlas and PAR-BS. Atlas is the simplest one because it requires only one counter per thread. And it's very hard to get beyond that, I think. PAR-BS is more complex than Atlas because it requires more counters. TCM is even more complex. Now, TCM can be made a little bit less complex if you do not do this niceness-aware shuffling. So if you do actually more random shuffling, randomized shuffling, you reduce the complexity. And I think that gets closer or less than PAR-BS. But you cannot beat Atlas, I think. Atlas will be very hard to beat. OK. Shall we take a break now? Guess we'll take were we going to take a longer break this time? Or it's 3 p.m., but